All right, hello physics fans. Today we're nearing the end of our fourth unit, and we've run out of time to talk about AC circuits in detail. But we'll try today to just give a little bit of a taste of that subject. Why are alternating currents so much more complicated than direct current systems? And it has a lot to do with the idea of phase. So, just to remind you, we are still in waveland. We are still trying to master the ideas of frequency and wavelength. And part of our goals for this week were to apply this to like musical instruments. And so you'll remember that our frequency has to do with the period. 2 pi. The frequency is 1 over the period. The angular frequency is 2 pi over the period. Our wave number is related to the wavelength, how long it is between two identical positions on a wave. And so that's 2 pi over the, our k is 2 pi over the wavelength. And so these two go into our expression where if we have both of these as positive, k minus a positive omega t, then that denotes something, a wave that's moving in the plus x direction. And then if one of those is negative, that would denote a wave that's moving in the minus x direction. So for instance, if I wrote, 3x minus 5t with some units, that would be moving in this way. If I wrote sine of 3x plus 5t, that would be a wave that was moving the other way. Okay, now the speed of that wave, we've also talked about how the speed is the wavelength times the frequency, or the speed is the angular frequency divided by the wave number. Those are two ways of saying the same thing because the 2 pi's, it turns out, just cancel out. Now, something else that we have talked a lot about on Monday of this week was how standing waves come from waves that are traveling in two different directions and interfere with essentially themselves. It's themselves in the sense that the wave hits some barrier and ricochets back. So this is a nice example where you have one end of a string that's pinned to a stand or something like that. So that is a node. And then you have another end that's being shaken, and that's also pinned so it counts as a node. And then the rest of this is able to go freely, but it turns out that you don't get this type of a nice pattern at every frequency. This only happens at a specific frequency for a specific tension of your string. And you'll remember that the speed of a wave traveling down a string of tension T and linear density mu is given by this. And so if you have a string of a given tension and given linear density, it'll have the same approximate speed for all these waves that you're sending down. And so what's special is if you pick a frequency or pick a frequency such that the wavelength that goes along with that frequency is just fitting into this space. So we were talking on Monday about resonances where you fit the wave to the space. And then of course, let's say that this were a guitar string or something like that. In that case, the frequency that goes well on the string will manifest as a louder sound because it shakes the air more around the string. Okay, so we're adding up one wave going one way, one wave going the other way. This is the not the lowest harmonic. It's the second to lowest harmonic. The lowest one would just be this, but this is a nice picture because we can see very clearly that this is one wavelength that goes up and down and back. Okay, a nice example of a standing wave that I think I shared this earlier in the semester, but it's relevant here again. If we simply take the rotating plate out of the bottom of a microwave and look up the frequency that the microwave is putting in that oscillating signal, you can actually measure the speed of light using a Hershey bar. This is from Twitter user David Barato. An example that he put up last year, where you put a Hershey's bar, and the places where you get the maximum intensity of your standing wave inside of the microwave, because the microwave is just setting up a standing light wave inside of that thing. The distance between these maxima, the places where the Hershey bar looks most scorched, are the maxima of that standing wave. That is not one wavelength, that is 1/2 of a wavelength. So what he's doing here is he's saying, okay, 1/2 of a wavelength is around 6 centimeters. So the wavelength is, so you can see here he's got the 6 centimeters, that's about 1/2 of the wavelength. So the wavelength would be 12 centimeters, or 0.12 meters. And then he just looked inside of the microwave and looked at the output frequency. So the output frequency is 2450 megahertz. So the frequency was 2450. Mega means million, so times 10 to the 6th hertz. And so if you take 2450 times 10 to the 6th times 0.12, you should get around 2.95 times 10 to the 8th. And that gives you the number of meters per second. Meters and hertz is 1/second, so meters per second. And the actual number is around 2.998 meters times 10 to the 8th meters per second. And so this is actually a pretty good estimate. We talked last time about how you could do a similar type of experiment with a tuning fork and water going up and down a tube to change the length of the tube. Okay, now this idea that if you sort of fit the wave to match the size of the container holding the wave, you can get lots of nice resonances when you have two clamped ends. So there's your first harmonic, and to go up to higher harmonics, essentially you're adding more nodes. So like this one, we added one node to go to from our 0th, so we still have both nodes at the end, and then you go up, and so every time you're adding in more nodes, you get to essentially a shorter wavelength. Shorter wavelength will have a bigger frequency. It's going back and forth more quickly. Okay, so for this is our case with two clamped string resonances. There are formulas that I will give you, but I think it's better to sort of draw the picture and reason it out. Then we have also the case where we have a pipe open that's open at both ends. So then both ends count as antinodes. So in this case, both of our ends were nodes. And here, both ends are antinodes. And this picture is just trying to draw your attention to the fact that the thing that's vibrating in this case is a little bit different. When we add our string, the thing that's vibrating is the string. When you have your open-ended flute, the thing that's vibrating is the air itself. And this does matter because the speed of sound moves much more quickly in solid materials than it does in air. You know, the air is not closely packed together, so it takes some time for the oscillations to be transferred from one part of the air to another. But the string is all of the material is nice and tightly compacted, so it's easy for the sound, that disturbance to travel through it. Interestingly, the opposite is true with light. Light, for reasons we will discuss when we come back from break, seems to travel slower through materials than it does through air. Okay, so there's our second case, is where we have two open ends. And then our third case is a little bit weird. You'll notice the equations are the same for clamp string resonances and pipe open at both ends. The difference, of course, is that V here in the clamp string refers to the speed of the wave on the string, and V in the other case refers to the speed of sound in air. It's a little different. If we have one pipe with open at one end, then that V also refers to the speed of sound in air, but we have one end, the closed end, that acts as a node, and then the open end acts as an antinode. And so, in fact, the waves that are fit in there are longer than the waves that fit in this the wave that has two open ends. So, for instance, if you take a open-ended flute and you put your hand against one end, it turns out that it will double the wavelength of the resonance frequency, and it will sound one octave lower. Okay, so here's a homework problem that I gave to you. It's not intended to be super deep, but it is helpful to think things through. It says, okay, pipe A is made to oscillate in its third harmonic by a small internal sound source. Okay, so remember, here we've got two open-ended open ends. In that case, our lowest harmonic would be like this, where we have our wave pressures going something like this. So if we are on his third harmonic, then this is one node. You'd have to go from one node to two nodes to three nodes. So in that case, it would be something like this, and our standing wave pattern would look something like that. Okay? Now, it says sound emitted at the right end happens to resonate four nearby pipes, each with only one open end. They are not drawn to scale. Pipe B oscillates in its lowest harmonic. Pipe C in its second lowest harmonic. Pipe D in its third lowest, and pipe E in its fourth lowest harmonic. Without computation, rank all 5 pipes according to their length greatest first. Okay, so I just want you to notice how this is working. This wavelength, so let me just write it this way. This here, from that to that, is the wavelength of the sound that's coming out of this tube. And it's the wavelength of the sound that's causing the resonance in each one of these tubes too. Now this is open at two ends. This is closed at one end. Now you'll remember the wave that allows this to meet its lowest harmonic is one where we fit in a quarter of the wavelength. So we have a node here, an antinode here. So drawing it roughly to scale, I would have just 1/4 of that wavelength, and so this tube B would be quite short. On the other hand, for the second lowest, we'd have to have one more node. So instead of being that short, so there's my B, there's my C, I'm going to have a node there, but I'm not changing the wavelength here. I'm keeping the wavelength the same because it's the wave from this source that's causing this resonance. and so C will have to be longer in order for that to occur. Okay, and so it says rank the 5 pipes according to their length, greatest first. Well, I can already rank these ones. I can say that B is is shorter than C, is shorter than D, is shorter than E. And when you do this, I encourage you to draw these in, and then you can compare the length of this pipe with the lengths of the third and the fourth. So presumably the wavelength of this will fit somewhere in there. So I will let you think about that, and you can finish that for your homework. All right, now the other thing that we've been talking about this week is we've just been dipping our toe into the idea of how this model of oscillation dovetails with all of the work that we've been doing recently, trying to understand oscillating systems. So the system that we're looking at to try to just get started on this idea of alternating current is the LC circuit. And this is sort of an idealized system because it doesn't have any dissipation of energy or anything. It just has energy being transferred back and forth between the energy in a capacitor, and then as the current drains out of the capacitor, it transfers over to being energy in an inductor, and then that current will recharge the capacitor the other way, and then that charged capacitor will discharge again, going and then that draining current transfers that electrical energy to magnetic energy in the inductor. So what's interesting here is that here in this picture, for instance, let's say this is 1, 2, 3, and 4. The energy of your this green is our energy of our inductor, right? It's going from 0 back down to 0, back up to a maximum, back down to 0. And so this is one total cycle, and it comes out of the current starting at 0, and then halfway through the current is 0 again. So you have a current versus time that looks something like this, where you have your current going one way, comes up to a maximum, starts decreasing, comes down to 0. When the current is 0, that's when your capacitor is completely charged again. Then the current starts going the other way, and then it starts decreasing and comes back to 0. And so these places where the current is 0 is where your capacitor is totally charged. The place where your current is maximum is where your inductor has the most energy. So this is a total cycle. The cycle is in the current going positive to negative. So 0, positive, 0, negative, 0. That's one total cycle. But you'll notice that the energy is going between the all of it's in the capacitor, all of it's in the inductor, all of it's in the capacitor, all of it's in the inductor, all of it's in the capacitor. So one total cycle goes through 2 cycles of sharing the energy between the capacitor and the inductor. That's the same thing that happens in the block and spring system, where the energy goes through 2 cycles of going from potential to kinetic to potential to kinetic. So that's an interesting convergence. And in fact, you can do everything where there's a direct map between the spring energy in your block spring system So that's where you have your spring and a block, and the block is moving back and forth. And at the edges, when the spring is most stretched and most squished, that's when you have the most potential energy. When you're at the middle, when the block is going through its equilibrium position, that's when you have the most kinetic energy. So in the case here, where we have a capacitor and an inductor, it's a little weird to think about, but this is like the spring, and this is like the block. And it has, this is like our kinetic energy, and this is like our potential energy. Okay, so you can make a pretty close analogy between the two of these, and just the same way that the spring constant and the mass are the two things that are you know, the dials that you can turn. Here we have the inductance and the capacitance. Okay, so just to drive this home, I gave you a homework problem that you may have looked at already. Let's just look at it together. It says, in a certain oscillating LC circuit, the total energy is converted from electrical energy in the capacitor to the magnetic energy in an inductor in 1.5 microseconds. So what I want you to notice is that this is one full cycle in this picture. And it says it takes 1.5 microseconds to go from all of the energy being electrical, so that's like this, to all of it being magnetic. Now the thing to notice is that is not one full cycle, because you go from A to B to A to B to A. That's one full cycle, going through that electric, magnetic. And so in fact, 1/4 of our period is 1.5 microseconds. Okay, so you have to take that times 4 to get your period. Then part B asks, what is the frequency of the oscillation? So once you have that period, the frequency of the oscillation is how long does it take the current to go through one full cycle. The current is going to go through one full cycle every period, and so the frequency is going to be just 1 over that period. Then part C asks, how long after the magnetic energy is a maximum will it be a maximum again? So part C, once you find that period, you can look at this and realize that the magnetic energy is a maximum every time the current amplitude is a maximum. So it happens here and there, and so it's going to be just 1/2 of the period. Okay, so I'll let you put in the numbers, but I hope the idea is pretty clear there. Now the other problem that we did in our last video is the idea of comparing the maximum amount of charge and the maximum amount of current, and in this case you can do that by using the energy, because the total energy stored in the capacitor here is equal to the total energy stored in the inductor there. So if you want, so in this case they give you L, they give you C, and they give you the maximum charge, so that's Q. This one's Q. And then they ask you to find I. Find that maximum I. And so that can be done by just setting these two equal, because when you have a maximum, this is going to be all UE. And when you have a maximum energy in the magnetic, you have a maximum current. And so you can just go Li squared over 2 is Q squared over 2C. And so all you have to do then is make sure that you're putting in your 10 to the minus 6 here, 10 to the minus 6 there for your micro, and then 10 to the minus 3 for your milli. And then solve for I. Now in this week's lab, we did something a little bit more complicated. And so I want to just sort of slow down and try to understand what we actually did this week in lab. Some of you have already done the lab, some of you will do it soon. So to make it more realistic, to make this system something that we can actually act on, we did something sort of interesting. We put in an alternating voltage source. So that's a voltage that looks kind of like this. So you get to pick that frequency, where that's 2 pi times the frequency. And the voltage is going up and down. So it's going between some maximum and some minimum. And when you put in a capacitor and an inductor, the resistor, we didn't put in an extra resistor, but you'll remember that the inductor, that big loop that we've been using, has some internal resistance already. And so if we want to think about questions like what kind of current are we going to get out at each frequency, or questions like how much power is being used by this circuit, it turns out that everything gets a lot more complicated with alternating currents than with direct currents. And the reason is that the current is not necessarily in phase with the voltage. Okay, so when you have a current, if you just had a resistor, these two curves, the voltage versus time and the current versus time, would be right on top of each other. But in this case, they might not be. It might be something like this, where you have a phase offset such that the current is not happening. It's not going back and forth in the circuit at the same exact time that the voltage that you're putting in with your alternating voltage source is going back and forth. So just to break this down, an RLC circuit has a resistor, an inductor, and a capacitor. If we just had a resistor, it would actually it would be easy, because our voltage goes up, our current goes up. Our voltage goes down, our current goes down. And so in that case, your voltage would be pointing in one way, your current would be going the same way. Voltage, current would just be going back and forth, back and forth, back and forth. And so if you just have a resistor, it's following Ohm's law like normal, no big deal. Now, where it gets complicated is with our inductor and with our capacitor. So, for instance, let's say I have my capacitor here, and the capacitor follows this rule that Q equals C times V. And so if I want to think about the current in this system, the current depends on Q because it's the time derivative of that charge. Current is how much charge is passing through any point per unit time. So if I wanted to transform this, it would be dq dt. So that's I. I'm taking the time derivative of both sides. I equals C, and then this would be dV dt. So let's say that I put in some alternating voltage source that looks like the one they have suggested here. So let's say that it's V equals some amplitude times sine omega t. If I take the derivative of that, it's going to, for one thing, bring out an extra factor of omega. So that's going to be V naught times omega. And then this is not going to be sine, it's going to be cosine. Okay, and so if I put this in now, I would get I equals C times V naught omega cosine omega t. Now, what you can see here is that the current is using a cosine function, the voltage is using a sine function, so those are offset by 90 degrees. They're offset by a quarter of a cycle. And what's interesting also is that this number out in front, this cosine omega t is just going between -1 and +1. This is your amplitude of your current. And it will depend on what frequency you have. Roughly, if you have a big enough frequency, your capacitor doesn't have enough time to charge, so it turns out you'll get a big current. If you have a smaller frequency, your capacitor has time to charge fully, and so the current turns out to be less. So in this case, we introduced an idea where instead of just using V equals IR for these amplitudes, we use V equals I some other thing. So this is effectively acting as resistance in the same way that we were using resistance. If you have a big capacitive reactance, that's what our X thing is here. You get a small current and vice versa. And so in this case, our XC, that capacitive reactance, is the ratio of the amplitude of the voltage to the amplitude of the current. And so our amplitude of our voltage here was just V naught. Our amplitude of our current was C V naught times omega. So you'll see the V naughts cancel out there, and this is just 1 over C times omega. Now what does that mean? It means that if you have a big omega, big frequency, you get a big current. So big frequency will give you a small reactance. Small reactance means big current, just like small resistance meant big current. Okay, now you get sort of a similar case here, but remember, an inductor is sort of acting in such a way that you have the voltage that it provides pushing back against the applied voltage depends on how the current is changing in time. So if you look at the picture that's provided in your book, it's going to be easier just to, because we're again going to be looking at how does the reactance change, how does the amount of current that I get change depending on the frequency. What if I put in a current that looks like the current they've given me, which is just I naught times, and this looks like a minus cosine function. Wait, is that right? IL is minus cosine. Okay, so minus cosine omega t. And so this depends on di dt. So in this one, if you take the time derivative of the current, it would give you derivative of cosine is minus sign, but we've got a minus sign on here, so this would be a plus I naught, and I have to do my chain rule, so I'm going to get an extra factor of omega sine omega t. Now, what's interesting here is that this is the factor that's going to matter. So if I look then at the voltage that's going across my inductor, this is my voltage, it's going to be something like minus L I naught omega sine omega t. And whoops. And this voltage, it turns out, is the induced voltage going backwards. So if I want to get the voltage that's being applied, the total sum of those around the loop is 0, so this would be minus. And so the voltage that's being applied there would be L I naught omega sine omega t. So that's what you can see right here. But this thing, it turns out, is the amplitude of my voltage. Sine omega t just goes between -1 and +1. So there's my amplitude of my voltage. I know my amplitude of my current is just going to be I naught. And so if I want to find my inductive reactance, that's where we're treating this as just like the resistance once again. My inductive reactance is just going to be the voltage divided by the current. So if I take my voltage amplitude divided by my current, so let me just say that. Here's my XL is my voltage amplitude divided by my current amplitude. It would be L I naught omega over, and then my amplitude of my current would just be I naught. So my XL, my I naught cancels out, would just be L times omega. So what does that mean? It means that if I have a big omega, I have a small I. So big omega means I have a big reactance. That's like resistance. Big resistance would give you a small current amplitude. And the idea there is that it's reacting to the change in current. So if you have a fast frequency, you've got a lot of change. And so that's going to minimize the amount of current that's able to flow through that inductor. Now this all gets very complicated because if you do a Kirchhoff loop rule and you put a resistor and an inductor and a capacitor in your circuit, they are all going to be out of phase. But I will tell you, electrical engineers have put a lot of thought and a lot of energy into these sorts of problems. So they have developed an entire math framework for dealing with them, and essentially it's transferring the problem of adding sinusoidal functions that are offset in phase to adding vectors. And those vectors they call phasors, and they do this with complex numbers, and I don't think that we need to master that in this course. Regardless, the interesting thing that comes out of this is that the current depends on the amplitude of the voltage that you put in, it depends on the resistance, it depends also on these reactances. And because the inductor leads the voltage and the capacitor lags the voltage, if you have their reactances matched, if you have the same amount of voltage across each one, essentially you can get those effects to cancel out. And that will lead to a resonance condition. So that's what we're actually studying in lab this week. I have you plot the reactance 1 over the capacitive reactance, which is just the amplitude of the current over the amplitude of the voltage, versus omega for the capacitor, and the slope is C. And then for the circuit with an inductor, I just have you plot the reactance of the inductor, so that's just your voltage divided by your current, and then versus the angular frequency, and the slope of that graph gives you the inductance. Okay, now once you have those two, you can find out what the predicted resonance frequency of that RC circuit is, and then we go ahead and measure it. And the way you measure a resonance is by looking at where is the current the maximum. Okay, so we just do that directly. You can try different frequencies and see where do you get the maximum current amplitude out, and it's a pretty nice direct lab in doing that. Okay, I just went and taught class, so I'm coming back a couple hours later, not knowing exactly what I said. In any case, so we're able to get the capacitance off of one graph, we're able to get the inductance off of another graph, we're able to plug those into this expression for frequency and predict what we should find as the resonant frequency, and then we're able to measure that, and so we can compare those two together. Now, when we're doing this lab, there is one thing that is worth mentioning that's a little bit confusing. Often when we measure things involving alternating currents or alternating voltages as well, the average of any of these values, because they're going back and forth between positive and negative, would be 0. So we don't really think about the average as much as we think about the root mean squared of the value. So what is that? That's like if we took this and we squared it, and then we took the average of that square, and then we took the derivative. So in any case, sorry, getting phone calls. This video is a mess. In any case, usually we report values in terms of this RMS. So for instance, if you ever heard that there's 120 AC volts coming out of the wall, that is the RMS frequency. And if you wanted to get the amplitude going, between the positive and negative, it doesn't actually go between positive 120 and negative 120. You would have to take that times the square root of 2 to get the amplitude. So it actually goes between about 170 and minus 170, somewhere around there in volts. And this turns out to be important because if you want to think about instantaneous energy being used by an AC circuit, the power would just be the current times the voltage. But in terms of the amplitudes, it's not, the power would not be the amplitude squared times the resistance, for instance. It would be the RMS, the root of the mean of the squared current that would give you that. So it's interesting to realize that the maximum current that you're getting is significantly larger than the RMS value. So I had intended to do a lot more on this video about transformers and the power system, but I think I'm going to put that off to the next video because we didn't get that far in class. And so let's just sum it up by saying that the phase matters. If you have capacitors and inductors, they are not necessarily going to have a current going through them that's in phase with the applied voltage, so it matters. The case in our LRC circuit, this particular circuit, where you do have everything in phase, the applied voltage and the current in phase, is where the reactive, the reactance, the capacitive reactance and the inductive reactance of the capacitor and the resistor respectively are equal to one another, and that's where you get this omega equals LC, 1 over square root of inductance times capacitance. And I think I'll try to hit a little bit of why we use AC power instead of DC power in our next video. All right, so I think this is already enough. Good luck. If you have any homework questions, please let me know.